This is our third lecture, and in this lecture, we're going to talk about buffering. So, what do we know about the disk? We know the disk is formatted into blocks, okay, blocks, and you can tell the operating system which block you want to access by giving its address. Okay, so address is just some unique identifier. So last time we said it's a pair. Um, and the pair tells you which track contains the block, and also what is the ID of the first sector inside the block, right? So it's a pair. Well, if you want, you can just think about it as an integer. That's the address, right? So if you got two pairs, I'm sorry, if you got a pair, you have two numbers, you can just look at the binary representation of the pair, right? So you can reinterpret the binary representation as an integer, right? So yeah, that's a simpler way to think about it. Okay. So anyway, from now on, which we are just gonna say, this block address is an integer. Okay. Well, all the blocks have exactly the same size, and this is measured in the number of bytes. And last time I said a very common block size is 4 KB, right? So that will be 4096 bytes. Good. So a very strong message from last week was that you don't really want to perform IOs that often because every IO is going to basically uh, cost you something expensive. No matter it's reading or writing, it is expensive because you have some mechanical movement involved in the process. So how expensive? It's you cannot really say exactly the same for every single IO, but over a sufficiently long period of time, you will be able to calculate some good average. And I would say 10 milliseconds would be a very convenient and reasonable estimate for the average. Okay, so 10 milliseconds, I emphasize, right? Because I get this a lot, right? Some students will say, hey, that's a very short amount of time. You won't even notice. Okay. Um, and you are right. You won't notice it. Okay, but you are not a machine. I can tell you 10 milliseconds is like a huge amount of time for CPU because CPU can do a lot of work within 10 milliseconds. Okay. But if you ask that question, it's a great question um, because so you have got the idea why CPU time is typically negligible compared to IO time. Right. So when we talk about database algorithms, indeed, we very, very seldom talk about CPU time. If you want to design a database algorithm, very, very seldom the design aims at minimizing CPU time, simply because CPU time is negligible. Okay, good. So remember that message. I think the message cannot get any stronger than that. Okay. So today, we're going to talk about this buffering technique. This buffering technique is something that's indispensable. If you want to have a good database system, you must implement this technique. Okay, so this technique can help you improve the I/O efficiency dramatically. Okay, all right. So hopefully, at the end of today's lecture, you will have a good understanding of this. All right, now let me start with a red box here. Okay, so this is really like a warning box, like strong message. So I want to tell you that a database query algorithm typically will have to access many, many blocks. In other words, the I/O cost okay, measure in how many IOs you want to perform, right? So the IO cost will have to be large, okay, for many queries, especially when we talk about join algorithms, and you will realize, it's really, really a lot of IOs there, okay? Well, people observed two very interesting facts in practice about how these algorithms, execute in practice. Um, the first fact uh, is um, the first fact is not just about one single query. You can imagine you asking a query and I'm asking a query, and our queries could be dealing with the same table, right? Same relation. So we our algorithms might be interested in the same set of blocks, and therefore it's easy to imagine that different queries would probably have to read the same block, um, you know, again and again. Okay, so you read it, I read it, and maybe another query will read it. So this creates some overlap, right? Overlap in the block accesses. Okay, so this is fact number one. And fact number two, even if you just talk about one query and look at the IOs that are performed by this query only, um, and you will see sometimes the query will have to read the same block more than once. Okay, so this is not surprising, right? So think about what happens in internal memory. Just think about, for example, sorting, the sorting algorithm, merge sort, I don't know, bubble sort, quick sort. Sometimes you will have to read the same number twice, right? So similar phenomena also exist when you are dealing with IOs. Okay. All right. So why are these two facts useful? Well, these two facts are useful because they tell you if you are smart, and perhaps you can avoid some of the disk accesses. You see, um, think about the idea of a very simple idea of buffering. Say with you issue a query, I issue a query, and you have to read a certain block. Let's say with address number one, okay, and I will also have to go there. So naively, the database system can perform two IOs for you and for me. But then think about the possibility of resorting to the main memory. So what if the database system is able to keep the block in the main memory long enough for my query to access? So you have to access the block first, and there's no way around it. The database system will have to pay one IO. That's for sure. But the thing is, if this block stays in the main memory, as I said, long enough to wait for my query to come along, right? So my queries is not aware of this, right? So my query says, okay, database, I want to read a block with ID one, and then the database takes over. But then the database is smart enough to see, hey, this block with this particular address is still sitting in the main memory. So why do I have to go to the disk to perform another IO, right? So we get to save this 10 milliseconds, right? So this is the idea behind buffering, okay? As you can see, this buffering idea works only if there are overlaps in the disk accesses, in the block accesses. By the algorithms. Okay, so sometimes multiple algorithms. If strictly, I mean, each algorithm accesses a disjoint set of blocks, and also, every algorithm would never access the same block twice, and then the idea of buffering is not going to work. Okay, but as I said, this is not how things are in practice, and in practice, we do have these two facts and they arise again and again. So this gives us opportunities to boost the performance of the system. Nice. So now we're going to talk about memory. So now you know that's interesting, right? So um, we are concerned with the disk, right? So that's our main concern. Um, However, to improve the disk, we need to work on not only the disk, but also, we have to work on the memory as well. Before I go into, further details about buffering, I'd like to give you an overview of the main memory setup in a real system. Okay, so because if you are not careful enough, this can sometimes be really confusing. Because the memory is really, really divided into a lot of parts. I don't want you to get confused about different parts. So here, this is one machine. Think about this as the database server, okay? And the white part here represents the disk of this machine. And the orange part here represents the main memory. Okay, so the disk is very large, but the memory is very limited. So let's say we've got 64 gigabytes here, something like that. Okay. So you have to remember the database system is just one software running under the operating system installed on this machine, right? So every software, every program running in the operating system gets allocated some memory. So this is the memory allocated to the database. Okay, so maybe let's say 10 gigabytes, something like that. Okay, so this light blue part. Okay. And then the same operating system might also have some other programs running. So these are the programs. This is the pink parts, the pink portions are the memory allocated to those programs. Okay, so database has no control over these portions. And furthermore, typically, if you want to access a database, you are not really running your program on the server, right? So just imagine you have your laptop and the database server is sitting, somewhere in NTU. So you don't really go over to the server and run your program inside the server, right? Instead, what you do is, you sit um, at home, and you use your laptop to connect to the database, right? So in this case, your laptop, your program actually runs on your laptop and it has its own memory there, right? So as you can see, when I talk about memory, um, you have to get very clear, which part, where this memory is, right? So don't get confused, right? When I say memory, for example, it does not refer to the little memory that you have on your laptop, right? I'm actually referring to the memory that is allocated to the database system. But the database system has a lot of use for memory. So as I said, the light blue part is all the memory that the database gets from the OS. I can tell you the database will allocate most of the assigned memory to serve as the buffer. Okay, so this is the cyan part. As you can see, it constitutes a majority of the allocated memory. So that tells you just how important buffering is to a database system. Okay, so next I'm going to talk about this buffer pool. Okay, buffer pool. So this is the cyan portion in my illustration here. Okay, so formally, a buffer pool is a memory array. So when I say a memory array, I emphasize on the fact that the buffer pool will have to be continuous. Okay, because when you talk about an array, instead of a linked list, we're talking about a contiguous portion of the main memory. Okay. So for example, this buffer pool could have the size of 4 megabytes. This is just really a toy example. Um, the size of a buffer pool in practice, is much, much larger than that. But, it's just a huge array with a certain size. Okay, so this array is divided into, what we call frames. Okay, frames. So frame is simply a smaller array inside this buffer pool. And every frame has the size of lambda bytes, okay, exactly the block size, okay. And therefore, you can see this is really not a coincidence because we want to use memory to retain some of the blocks that have been accessed by the database before, right? So we want to retain those blocks. And therefore, you want to have a one-one correspondence, right, between frames and blocks, okay? In fact, some people just say block, even though they are referring to the buffer pool. In my opinion, it would be nice to use two separate terms so that, whenever I talk about frame, immediately that I'm talking about something inside the buffer pool. Okay. So I think this is going to make it clearer. However, other than that, a frame, you can think about it as like a memory, as like the memory counterpart of a block on the disk. Okay, so that would be quite helpful. Okay, so for instance, if the block size is 4 KB, okay, so that's 4096 bytes, and if the buffer pool has the size of 4 MB, and then how many frames do you have? It's a 4 MB divided by 4 KB, so that's 1024 frames. Okay. All right, so that's the buffer pool. Okay, so you can think about the buffer pool as a sequence of frames. Okay, so every frame, just has the size of a block. Okay. Now let's talk about one particular frame. Every frame is either empty, which means it's not being used, or it stores the contents of a block. Okay. As I said, right, this is reserved strictly for the purpose of retaining blocks. Okay, you don't use frames for other purposes. Okay, so either you don't use it, or when the database system uses it, okay, it's always used to store the contents of a block. So I said you don't use it. I mean, strictly speaking, I should take that back. It's you as a user have no control over the buffer pool. So the buffer pool is managed by the database system. Okay, so I should say the database system would either leave a frame empty, okay, or it would put a block into the frame. Okay. All right, so if that's nice to you, if that's clear to you, and then we can talk about the reading process. You see, without the buffer in the middle, the reading process would be very simple, right? So if you want to, if an algorithm wants to read a block with certain address X, and then you simply access the disk directly. Okay, you tell the piece of hardware saying, okay, here is the block address, and I want to fetch the contents of that block. Okay, so this is simple. However, you miss the opportunity of saving this IO. Okay, now we have this buffer pool in the middle. The reading process becomes something that's more sophisticated. Okay, so let's look at these 4 steps together. So the first step is to check whether the block is currently in the buffer pool. Okay, so if it is, it will have to be in some frame, right? So the database keep tracks of the addresses of the blocks that are currently in the frames. Okay, you don't have to worry about how. I mean, there are different ways to implement this. It's not really the point here. But the point is, if the block is indeed in a certain frame, and then we have something nice here. We have a buffer hit. Okay, so congratulations. Now you can save the 10 milliseconds. Okay, so in this case, it's all done. So the database simply returns the contents of this frame to you to this program, and then everything's done. Okay, and then there are no more steps. Okay, skip the steps. Well, things get a little trickier if this is not the case. Let's say the block is currently not in the buffer pool. And then, of course, the database will have to do the dirty work. It will have to do the hard work. So it will have to go to the disk to perform an I/O so that the contents of the block can be fetched from the disk, right? So 10 milliseconds out. So in this case, we say that we've got a buffer miss. All right, but now that you've got a new block just read, right? You just read a new block. The database system would try to retain it because the idea is since we have already read it, right? And it's something that we have read recently. Very likely, another program is going to use it later, or maybe the same queries algorithm will have to read it later. So let's retain it for a while. Okay, let's just retain it for a while instead of throwing it away immediately. Okay, so for that purpose, you will have to find an empty frame to store the block. Okay, so if the buffer pool is not full, which means you can find an empty frame and then all good, right? So you simply copy the contents of the block into the frame, and that's it, right? So that's the easy case. On the other hand, if you cannot find any empty frames, so this means the buffer pool is full, right? So in this case, what you have to do is to evict, this word evict, right? Evict. So you have to evict evict an existing frame. Okay, so you say, okay, this frame, the block inside, it will have to go. Okay, and then this frame, I will have to empty it. Okay, and then now you have make an empty frame. You have created an empty frame. So now you can place the block you just read into this empty frame, right? So here, clearly, there's something non-trivial going on, right? So there's buffer replacement, right? And this has a big impact on the performance of the buffering. We're going to talk about this buffer replacement later, but at this moment, you can treat it as a black box, and this black box simply saying, when the buffer is full, there is this program that you can call. This is a utility program, and this program is going to create an empty frame for you. Okay, so you want an empty frame, and here it is, right? So that you can continue the process here. Okay, and finally, of course, you have to return the block's contents. Okay. All right, now here is an example. So let's just say that our pool is very small. It has just 4 frames. And currently, we have 3 of them occupied. And here, I'm showing you the address of every block that's inside the buffer pool. Okay, so this is 63, this is 28, this is 109. Okay. Now let's suppose that we receive a read request. Okay, read request. So this request is to read block 28. Okay. Now the system checks the frames. Indeed, 28 is here. Ah, good news. So we get to save this IO. Okay, so this is done. All right. And then the next request comes. Let's say the request wants to read another block, block number 12. This time it's not in the buffer, right? So you know what to do, right? So the database performs one IO to get the contents of the block. But then it will also find an empty frame to retain this block in the buffer pool. Okay, indeed, we have an empty frame here, so that's why 12 goes there. Okay, pretty simple so far, right? All right, so that is about reading. Now let's talk about writing. Okay, writing is slightly more complicated because it will have to we'll have to bear in mind that if you change the content of a block in the buffer, you have to remember this is not the ultimate purpose. Okay, so the ultimate purpose is to change the contents of a block on the disk. So you can write the changes into a frame because you want to save some IO. This makes sense because you don't want to perform one IO to flush the update modifications to the disk immediately because maybe another change is going to take place pretty soon, right? So why do you have to perform the IO twice if you have two consecutive changes, right? So you could buffer the modification inside the main memory, inside the buffer pool, right? But then you have to remember that eventually those changes will have to go to the disk, right? So this means that some bookmarking must be done regarding the blocks that have their contents changed. Okay, so this is where this notion of dirty comes into the picture. So formally, we say a frame is dirty if its contents are no longer identical to the contents of the corresponding block. Okay, so this is a very important concept. So it appears here. Okay, before the writing process. Now we are ready to talk about the writing process. Say a program wants to write a block with address X. Okay. So in this case, the database does the following. So first of all, the database checks whether this particular block, remember we have the address here. The database checks where this particular block exists in the buffer pool. If so, then we have a buffer hit, okay? And then the database simply performs the modification in the main memory, all right? So now the frame is updated, okay? So once the frame is updated, so you can imagine that the frame's contents will no longer be the same as the contents of the corresponding disk block, right? So the disk block actually becomes outdated, okay? It becomes obsolete. All right, so that's actually the incorrect copy. The correct copy actually sits in the main memory. Okay, but don't worry, the database will not forget about this update because this writing process is going to make the frame dirty. So you can, so the program does not have to do this. Okay, so this is the program doesn't have to worry about marking anything dirty. From the perspective of the program is just performing a write. Okay, and then the database says, okay, now I take over, consider it done. All right, so the program from the perspective of the program, the moment when the database says, okay, I have received your request, so the program's job is done. Okay, so program can take it for granted that eventually the changes will be pushed to the disk. So all these things are taken care of by the database system automatically. So this is the database's way to bookmark which frames will have to be written to the hard disk eventually. Okay. All right, so that is the good case, right? So the good case says the block is in the buffer pool. Now let's look at the unfortunate case. What if we have a buffer miss? So in this case, what the database does is not to perform the I/O right away. Okay, because you are writing, you are not reading, right? So if you are reading, like before, the reading process, in a buffer miss, you will have to perform an I/O right away, because otherwise, how do you know what is the block that the program tries to read, right? But here, you don't really have to perform the write right away, right? So you are the database, and as long as you are sure that you will eventually write this block to the disk, it will be fine. But you don't have to do it now, right? So indeed, this is what the write process does. So the process says, okay, so in this case, I'm not going to write the block immediately. Instead, I'm going to find an empty frame, and then I put the new block there. Okay, the new contents of the block there. But of course, I have to mark the frame as dirty so that I can remember that I still have to write this thing into the disk. But you could still run into the issue where there are no empty frames currently, right? So in this case, the buffer pool is full. In this case, again, you launch this buffer replacement program. Once again, we're going to talk about this program later. But what this program does is to create an empty frame, right? And then this write process can proceed to put the new contents into that frame. Okay, so this is the end of the write process. Well, now here, this is a red box, which means this is like a warning message. This is something very important. Okay, so eventually every frame will be emptied, right? So let's say during buffer replacement, or when the database shuts down, eventually all those frames will have to get emptied. So if a frame is dirty, and then the database will eventually perform an I/O to write the contents of the frame into the corresponding block on the disk. Okay, so this is a rule. Okay, without this, you will be losing information. Okay, good. Now let's look at an example. As before, let's say we've got a pool with 4 frames. Say the first request is to write this block number 28. As you can see, before the write, these 3 blocks, they are colored in light blue, indicating that all of them are clean. And here, after this write process, you can see 28 right before it was clean, but now becomes red, indicating it's dirty. Okay. So if a frame is clean, and then you can simply empty it, because a clean frame will have to be identical to the corresponding disk block. Okay, so you don't have to worry about information loss. So you perform. However, if a block is dirty, as I said, eventually you have to perform an I/O. Okay, so this is just some bookmarking that a database system does just to make sure that everything's done in the right way. Okay, so that's the end of the request for 28. Now another request comes along, and this time we want to write to block number 12. Now remember, we're not going to perform the write right away. So we will try to find an empty frame and simply keep the new contents inside that frame, and that's it. So if I ask you in this process, how many IOs, I mean in the entire example, right? To write requests, how many IOs have been performed? The answer is zero. Okay, the answer is zero. So now you can feel the power of buffering, right? So if your buffer is really, really large, and then you can imagine, a lot of IOs can be saved, can be prevented, right? This is actually really, really a great idea, right? I can think of many reasons why, these two blocks will be accessed again. Right? Okay, nice. So where are we so far? Well, you already understand the big picture. You understand the motivation. You also understand the general um, processors for reading and writing. And one thing we have not touched upon is this buffer management. Okay, so far we've been saying, this is just a black box you don't have to worry about, and this black box creates an empty frame when the buffer is full, or the pool is full. Okay, so next we're going to talk about how this buffer management works. Okay, so this is not easy. This is not a trivial task. Okay, so we will spend quite some time on this. Okay, so the organization for the rest of the lecture is the following. First of all, we're going to look at an omniscient algorithm. So as the name suggests, right? Omniscient. So this means the algorithm knows everything. Okay, so this is really like a hypothetical algorithm that exists only in theory. Because in practice, no algorithm will be able to predict the future. Okay, you will know the meaning of this omniscient very, very soon. So this algorithm really cannot be implemented. However, this algorithm tells us, ideally, how you should be performing this buffer management. So that really sheds light on the underlying principle for this buffer management, for doing this management well. And then we're going to talk about 3 algorithms that actually can be implemented. And these algorithms essentially try to simulate what the omniscient algorithm would be doing. Okay, and then this should give you a pretty good understanding about why things are designed the way they are. Great. Now let's start with this omniscient algorithm. Okay, so next, let's model this buffer management as a mathematics problem. We will be talking about some really cool guarantees, and that would not be possible unless we have some formalization. So I defined, let me introduce this so-called offline buffer management problem. Here we've got a pool, buffer pool with a certain number of frames, okay, n frames. And here we we do not really care about the contents of the block that are inside the pool because we're mainly concerned with buffer hits and buffer misses. So for that purpose, it suffices to worry about just the addresses of the blocks, right? Whether it's a hit or a miss. So for this reason, we're going to use, P1, this is the block ID, okay, the block address of the first frame. And P2 is the block address of the second frame, so on and so forth. Okay, so P1, P2, all the way to PM. Well, of course, a frame can be empty if frame is empty and then there's no address there, right? Then we use this special symbol. This is the empty symbol. Okay. So we'll be talking about just read requests, and therefore no frames will be dirty. Okay, all of them are clean. Okay. Um, well, as I said, the purpose is to really understand what is the underlying principle behind buffer management. Okay. So we can keep the problem as simple as possible so that we can focus on the core. So the objective is to serve end requests, and we know all the requests in the future. Okay, so this is really like an offline problem because this is not something that you know online in reality, right? But let's just say, omniscient, right? We have all the knowledge. We can predict perfectly what are the addresses that will be accessed in the future. Okay? And all of these requests are read requests. Okay. There's one constraint though. So before a block can be read, the block will have to be loaded into a frame. So this is fair, right? Um, you cannot say I bypass the buffer and then I serve the request. So that doesn't make any sense. Okay, so the block itself will have to go into one of the frames before you can say, okay, I have served the request. Okay. All right. So we want to have a strategy to manage our pool in order to minimize the number of buffer misses. Okay, buffer misses. Okay. So let me tell you why the problem is non-trivial, right? So let's consider a very simple case where m is just 2. Okay, so you've got two buffer. Okay, you've got two buffers. So say you serve the first request, A1 will have to be inside the frame um, to be served, to be read. So A1 is there, and now it comes to A2. Of course, A2 will also have to be there. So simple, very simple so far. Now let's look at A3, right? So immediately you are facing a difficult situation. You know A3 will have to go into the buffer according to the constraint. But the thing is now you have to kick out either A1 or A2. All right, so this is a big decision. Okay, because if you lose A1 and then next time when you read A1, you have to suffer from a buffer miss. Okay, so it's a big decision to make. So if you think about it, it's not really clear what you should do in order to minimize the total number of buffer misses overall, right? For the entire sequence of requests. Okay. Well, it turns out that there is a very elegant algorithm for solving this problem. This is Baladi's algorithm. Well, this is the English pronunciation. I think the exact pronunciation could be Baladi, something like that. Okay, but I'll just go with Baladi. So this Baladi's algorithm says, okay, all you have to do is to follow a simple greedy strategy. Okay, greedy strategy. Okay, so um, we are given the requests one by one, right? We start with A1 and then we serve it, and then we're given A2, A3, etc., right? So let's just consider um, something in general, the general situation. So we have already served a number of requests, and now we have to serve the next one. The next one's AJ. Okay, so for some J. Okay. Well, the algorithm has only 3 steps. First of all, you want to check if AJ is in the pool currently. Okay. So if AJ is currently buffered, and then all good, right? So this is a buffer hit. So congratulations, just save $1, right? So in this case, you simply, just return, right? Because there's nothing else to do. Okay, you have already served the request, right? It's in the buffer, right? It satisfies the constraint. Okay. Well, now when you go to when this if condition does not hold, right? You go to line 2, step 2. So as long as you go to step 2, a buffer miss has already occurred, right? You don't hit, right? So you missed. Well, in this case, you have to find an empty slot to store this AJ, right? You must do it according to the constraint, right? Because you cannot say, I read AJ, but I don't keep AJ in the main memory, right? So that's not how a database system works, right? So database system says, you always have to bring it into the main memory so that CPU can read it, right? So in this case, you must find an empty slot, right? So now the question arises, right? Do you have an empty slot? If you do, right? So this is stated here, right? So if you do have an I, some I, in this range, right? So in your pool, if this frame is currently empty, and then all good, right? So you can say, okay, I use this frame to store this block. I suffer from one buffer miss, right? So I do this, and then I have satisfied the constraint and done. Okay. The most difficult situation happens when the buffer is full. Okay, the pool is full. All right, so all the frames are occupied. So in this case, you are forced to evict an existing frame. All right, you have to kick out an existing frame. So now the thing is, you have to make a choice here, which of the existing frames to kick out. Okay. Well, as I said, Battle-based algorithm is a greedy algorithm. It simply says, you know what, you look into the future. Okay, which frame? I mean, you look at the next axis of each frame. Okay, next axis, not the past axis, right? The future axis for every frame, all right? So which frame will be accessed, the latest into the future, the farthest into the future, okay? And take that frame. Let's say this frame is the kth one, for some k between 1 and m, right? Kick that out, and you store the new block AJ in that frame. Okay. So this is the algorithm. We'll see an example to illustrate the algorithm, but if you want the formal description, here it is. Okay. All right, now let's see how the algorithm runs. So in the beginning, let's just say that P is empty. Okay, so nothing yet. All right. So the sequence of I/O requests is this. Now remember, all these are addresses. Okay, so as you can see, it's pretty long, right? 10 of them, and some addresses appear multiple times. So if the algorithm is good, we should be able to have some buffer hits, so that we don't have to incur 10 buffer misses, right? So 10 buffer misses is the worst you can do, okay? So we hope to minimize the number of buffer misses, okay? So in order to indicate which request I'm talking about, I'm gonna, add some time stamps here. So you see 10 time stamps, okay? All right, so when I say time 1, I'm talking about this request 17. Okay, good. All right, so now let's maintain this P. Okay, so this P, this is an array. All right, so there are 3 slots. Okay, currently all of them are empty. Okay. All right, so now let's process the first one. So the first request is 17. Okay, so 17, 1 miss, right? 17 is not currently in the buffer, obviously, so we have incurred a miss. And then we have to bring the block into the buffer, and we can do that because there are, empty slots there. So we put 17 here, okay, and we're done. Okay, so this is the first request. That's pretty easy. Now let's go to time 2, and then we're talking about 28. 28 is not in the buffer currently, and too bad, we have another miss. Well, nothing we can do about that. But we have to get 28 into the pool. We are able to do that because we still have 2 empty slots. Feel free to choose one. Let's just say that 28 goes here. Okay, so far so good, right? Okay, time 3, 13. Okay, another miss, all right? Well, so be it. And we still have 1 empty slot, so we put the 13 there. Okay, no problem. So time 4 gets interesting, gets more interesting. You see, time 4, we see another 17, right? But this time, no miss. Hey, we have 17 there. So we have a buffer hit here. Okay, that's pretty good. Okay, we don't do anything, you hit and then you are done. Okay. So time 5 now. The request is 53. First of all, do we have a hit? No, we don't have a hit, right? So we've got a miss. That's fine. Okay. And then we have to store this 53, right? So that's a constraint. Remember, we must get the new block into the buffer, okay, before we can say, it's served. But wait, you see, we don't have empty slots here. We have to kick out something. Okay, we have to kick out something. We've got 3 choices here, right? 17, 28, 13. Which one do you want to kick out? Okay. All right, so Ballady says, remember, greedy. You want to be greedy. Okay, look into the future, right? So see which block will be accessed again farthest into the future. All right, farthest. Okay. Well, let's see. Okay, 17, right? 17, it will be accessed because this is the current time. Okay, 5, right? So it will be accessed at time 9. Okay, so let me put a little remark here. So this is time 9. So this is the next access time. Okay. How about 28? Well, you got a 28 here, but don't forget you also have a 28 at time 6. And therefore, the next access time for 28 is 6. Okay. How about 13? 13 is here. You see? So the next access time for 13 is 8. Greedy, 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 right? Ballady says, go for the one with the largest, farthest next access time. So that will have to be 17. Okay, so that's why we say bye-bye to 17. It's gone, and we create an empty slot, and we welcome 53 into its new home. Okay, so this is the situation so far. Okay, so far we have 4 misses. Okay, 1, 2, 3, 4. Okay, so let's continue. Okay, let's continue. Okay. All right, so let me just write down the remaining requests for you. It's 28, 109, 13, 17, and 28. Okay, the timestamps, this is 6, 7, 8, 9, and 10. Okay. And currently, what's the buffer? The buffer is P, and then 53, 28, and 13. Let's see if it's correct. And yes, okay. All right, so the next one, time 6, the request is 28, 28. Okay, no miss, right? We got a hit. Okay, very nice. We must be doing something right then. Now moving on, time 7, we got a 109. So unfortunately, that's a miss. Okay, so again, we have a decision to make. We have to kick out one guy. So which one? Well, this time the decision is easy. Decision is easy. Okay, because look, 53, right? We'll never get access again, right? So currently, you see this is the time. We're at time 7. You look into the future, right? You don't see 53. All right, so 53 would never get accessed again, and therefore it's out, right? So this is an easy and obvious decision to make. And then we put 109 here. Okay, so this is the current P. All right, so moving on to time A, now you get 13, and that's a hit. Very nice, okay. All right, so now we come to time 9, that's a 17, that's a miss. We have to kick out somebody, okay. Well, here you can see 109 is obviously a candidate to be removed because 109 will never get accessed again. Actually, you could also remove 13 because the next access time for 109 is infinity as indicated here, but so is the next access time of 13. Okay, it doesn't really matter which one you kick out. Both are correct. Let's just say that we remove 109 and then, we put 17 here. Okay. Okay, so finally we come to the last request, which is 28, and that's a hit. Okay, so overall, we hit how many times? You see, we hit here, 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 and here. Okay, so 10 minus 4, and therefore we have 6 misses. Okay, so that's Baladi's algorithm. Okay, well, Baladi's algorithm is actually very nice. I can prove to you that Baladi's algorithm optimally solves the problem, which means, you are not able to design another algorithm that is able to reduce the number of misses any further. Okay, and it's true with respect to any sequence. Okay, any sequence. All right. I can prove that to you offline, let's say. But the proof is not required in the tests. Okay, so this is an optimal algorithm. Okay, optimal algorithm. Okay, but okay, so that's pretty nice, right? If we could implement Baladi's algorithm in practice, it solves all our problems, right? But no, Baladi's algorithm is an omniscient algorithm. It cannot be implemented, right? Because you have to know all the future requests in order to implement this algorithm, which you don't, right? You cannot predict what's going to happen, right? In most cases. So this is just a theoretical, hypothetical algorithm. So it's not really useful for practical use, okay? But why do we want to discuss it? Well, the reason is it tells us a lot about the principle of what we're supposed to do. Okay, so the principle is, we should try to evict, we try to throw out, kick out, right? Evict the frame that will be needed again farthest into the future. Okay, so the next access time, the next access time is the greatest, all right? So it's farthest into the future, all right? So that's what we're supposed to do. Okay. So this is in theory, right? So let's go back to the reality, okay? And now we are facing the online version of the problem, okay? So you remember, right? Baladi is for offline buffer management, but here we're talking about online, okay? Online essentially says, I just give you the next request. Now here's the next address, right? But that's it, right? You don't get to know all my future addresses, request address. I don't know how to say this. You don't know that all my future requests. Okay, so you have to make an instant decision without looking into the future. Okay. So we're gonna talk about 3 algorithms. The first one is FIFO. FIFO stands for first in, first out, right? So the rationale behind this FIFO says, hey, you know what? Let's adopt a heuristic. Heuristic. I don't know if you know this word. Heuristic. Okay, a heuristic basically says, well, it's just something that's probably true, but we cannot prove it. Okay. So the idea here is, okay, if a block entered the pool long time ago, it's an old block, okay, and maybe, just maybe, right? Perhaps it would not be accessed anytime soon. All right, so that's sort of like just a heuristic, as I said, right? So it's it's a conjecture, right? It may not be true. I mean, you can definitely um, create counter examples to prove me wrong, but still, this FIFO is something that's not completely unreasonable in practice. Um, Indeed, right? I mean, if there's some very cold block. When I say cold, I mean it's like unpopular block, right? So not too many queries will bother to read that block. But if occasionally, from time to time, some weird query would touch that block, but just once, and then for a long time, no other queries would touch that block. You could have situations like this, right? So this is basically the rationale behind FIFO. Okay. All right. So now let's talk about this strategy, more formal, right? Okay. So remember, we've got frames, right? We've got a lot of frames in the pool. For every frame, okay, so let's define an entry time for the frame. Okay, so if the frame stores a block whose address by ID, this should have been address with address X, and then we say, the entry time of this block is the time um, um, that it entered the frame. Okay, so this is just another way of saying things. Okay, so we'll see an example, and then things will get very clear. Okay, so you can look at the sentence. This sentence is a more formal way to say what I just said, right? But very informally, I would say, that's just the time the frame entered the block entered the frame. Okay, you will see what I mean. Okay, so that's the entry time. Okay. All right, and then FIFO says, okay, if somebody um, arrived earlier, and then it will be removed earlier. Okay, so that's why FIFO, right? So that's the strategy. All right, so let's use exactly the same sequence to demonstrate FIFO. Okay, so this is the sequence of requests. Okay, however, FIFO is an online algorithm. It's not like Bellody, right? Bellody's algorithm is an offline algorithm because it has to look into the future. FIFO never needs to look into the future. Okay, let's see. All right. So let's once again um, maintain our pool here. So we've got 3 positions, right? Now these are the timestamps. Okay, so time number 1, the request is 17, right? All right, so that's a miss, right? So we put 17 here. It's not a problem. Okay, so here, you see, this is the moment when the block enters the pool, right? So this is the entry time of 17. So I'm going to put a remark here. So this is the entry time, right? So this is 1, right? In my slides, this is discussed here. Okay. So 17 enters the pool. All right, now time 2, you have 28 here. Okay. So it's once again, it's a miss. All right. Nothing we can do about that. So we have to get the block into the into the pool. So this is the time the block enters the pool. So its entry time is 2. Now continuing, we get to 13. So this is 13. So its entry time is 3. Okay. So far 3 misses. Okay. All right. The next one, 17. This is a hit. You can see 17 is there, right? No problem. Okay. All right. So time 5. So this is done. So time 5, we get 53, right? But now the buffer is full. So we have to kick out somebody. All right. But now we do FIFO. All right. We do FIFO. So FIFO says easy, right? Who arrived first? The earliest. Okay, so you can see the entry time here, 1, 2, 3, right? So 17 is the block that arrived the longest time ago, right? So we say we evict the block with the smallest entry time. Okay, smallest entry time. So the oldest. Okay, so this guy's out. Now we've got 53 in. Okay, so what's the entry time of 53? That is 5. Okay, that is 5. Okay, very nice. Now let's continue. Okay, let's continue. So here, this is continuing. Okay, so I have the request here. So I'm not gonna list them again. Okay, so time 6. All right, so that's 28. Good news, that's a hit. All right, so no issues. Now time 7, we've got 109. That's a miss, so we have to kick out somebody. Okay, so again, we kick out the guy that arrived the longest time ago among the 3 in the pool. So it's 28, and therefore 28 is gone. Okay, so we replace that with the new guy, 109. And we have to record the entry time as well. So that is 7. Now continuing, time 8, and the request is for 13. That's a hit. Okay, time 9, the request is for 17, so that's a miss. We have to discard somebody, and this time it's 13 that is to be discarded. Okay, we put 17 here, and the entry time is 9. Okay, continuing 10 time to request 28. That's a miss. We have to evict 53. Its entry time is the smallest currently, right? So it's 28 and the entry time is 10. So this is how the algorithm runs, okay? I think that should be pretty clear, right? So that's the first algorithm, FIFO. Okay, so now let's move on to talk about LRU, which stands for least recently used, okay? So I can tell you this LRU is a very popular algorithm. Actually makes a lot of sense. Okay, so it remember, right? How all these algorithms they try to simulate biology. Okay, because you know the principles there. The principle is try to kick out the block that will be needed for this into the future, right? But the thing is, you cannot look into the future, so you just have to take a wild guess, right? So LRU, sorry, FIFO, LRU, and also this another algorithm we're going to talk about later, this clock algorithm, all of them are just doing wild guesses, right, in different ways. So LRU says, okay, you know what? I will see which block was last accessed, you know, longest time ago. Okay, so this is different from arrival. Okay, last access. You see what I mean? Because maybe a block can be very old in the sense that it could enter the block, enter the pool like 1 year ago. Okay, so that was a long time ago. But the thing is, maybe it's very recently accessed. You see what I'm saying? Okay, it could be accessed just like in the last minute, right? So this block would be a very low priority block in FIFO because that would probably be the next one to evict. But for LRU, such a block would be precious. Okay, so this actually makes sense in practice because in practice, the accesses performed by different queries, different algorithms, they actually tend to have some sort of locality. Okay, locality. So for instance, if some part of the database becomes so popular and this part could get queried again and again. Okay, so in this case, the LRU would make sense, right? It would say, okay, this block, I don't really care when it was brought into the pool, but if this is a block that a lot of people want, and then we might as well just keep it, right? So this is the rationale behind LRU. Okay, but I emphasize, right, this is just a heuristic, and you can easily create counterexamples to prove that this is not the case. So before we talk about LRU, we have to define this so-called last access time, okay? And I'll just use LA as the short form, right? LA, not for Los Angeles though, LA, okay, last access. So it says, okay, if you look at a frame and if this frame, stores a block with this ID X, this address X, and then the last access time is the time of its most recent request. Okay, so when was the last time you needed it? Okay, so that is the LA time. Okay. The larger the LA time, the more recent the block was accessed, right? The more recently the block was accessed. So the LRU, least recently used, right, says, okay, I want to kick out the frame whose block has the smallest LA time. So that basically says that was the longest, its last access was the longest time ago. Okay. All right, so let's apply this algorithm on the same sequence again. So we've got 3 slots, right? Okay, so time number 1, so that's 17. That's a miss, so 17 goes into our pool. And we have to record the last access time, right? So this is the current time, the LA time. So this is 1, all right? Because 17 is needed right now, right? Okay. All right, so moving on, time 2. So that is 28. 28, that's a miss. All right, so it enters our pool because we have empty slots there. And the LA time is 2, right now. So time 3 is 13. It goes into the pool. And the LA time is 3, okay? All right, now continuing, time 4 is 17. 17 is a hit. So now we have to update the LA time, right? The last access, right? So now is the last access, okay? So the LA time is goes from 1 to 4, right? We have to bump it up. So time 5, we got 53. Okay, 53. Now that's a miss, right? And too bad our pool is full. We have to kick out somebody, right? So 28 is the one to kick out here, right? Its LA time is the smallest. So we kick that out and we put 53 here. Now remember, you have to record the LA time, which is 5. Okay. All right, we're going to continue on the next slide. Copy and paste. Okay. All right, so continuing, the next one is 28, miss. Okay, we kick out 13. So this is 28 and LA time 6. Okay, still the next one, 109, miss. Too bad, a lot of misses. And then we kick out 17. So 109. Okay. This is 7. Okay, other time. Okay, continuing. This is the third time A, and it's a 13. We just kicked it out 2 timestamps ago. Okay. Well, unfortunately, another miss. Okay, so we kick out 53 and we put 13 here, and the elder time is 8. Okay, you get the idea, right? But anyway, let me finish the example. So the next one would be 17. Again, something we kicked out 2 timestamps ago. All right, so this time we kick out 28. I was just not so lucky with LRU. Okay, so time 9. And the next one's 28. We just kicked out 28, huh? Well, that's a bit sad. unlucky. Anyway, so 28, this LA is 10. Okay. So how many misses have we got? We have got just one hit, right? Here. So that's a hit, right? But we missed all the other requests. So all in all, we have 9 misses. Well, actually, the example was deliberately designed this way to debunk a common misconception that FIFO is worse, always worse than LRU. That's not true. Okay, so you have just witnessed a counterexample. Okay, I can tell you in practice, LRU makes more sense than FIFO. Okay, that is a fact. Okay, this is also the reason why a lot of much more systems, actually, I would say no, I haven't seen a single system that uses FIFO. Although FIFO is an interesting strategy, it actually has some theoretical guarantees, but in practice, to be honest, I haven't seen a single system that uses FIFO. Okay, I'll be happy to get corrected here though. Um, the LRU is much more popular simply because of the locality that I talked about. Okay, so indeed, accesses in practice they do have locality. Okay, so as I said, right, if a block is recently used, and actually especially if it's used again and again, right, so that serves as strong indication that this is an important block, and you don't want to kick it out. Okay. So anyway, so that is LRU, but theoretically speaking, you are able to construct sequences where LRU actually performs worse than FIFO, right? Mhm. Okay, so finally we have clock. All right, so this is the last algorithm we're going to talk about. Again, the clock is trying to uh, simulate what Ballady does, right? So the principle is there, but it's based on a rationale that is somewhat different from LRU. Okay, it's similar to LRU in the sense that we also look at the last axis, but the thing is, LRU says, I'm going to um, remove the block whose last access was the oldest. You see what I mean? So that was what LRU does, right? But clock says, no, let's forget about oldest. Okay, we don't want the what's the English? Superlative. Superlative. Yeah, we don't want oldest, right? We want, just old enough. Okay, old enough, right? You understand what it means, right? So you would remove some block that is very very old. So there is some sort of like a threshold, even though you're not really removing this oldest. You don't want this superlative here. Okay. All right, so let's talk about this. Let's talk about this um, clock in further detail. All right. So you know what? I will skip the formal description for now. Let's jump right into the example. And we will first get the main ideas, get the crucial ideas from this example, and then we're going to go back to the formal description to understand everything. Okay. So here, let me demonstrate this algorithm for you. Um, Again, 3 positions, all right? And you're looking at the same sequence as before, okay? So here, um, in addition to just the frames, this algorithm will also need to maintain 2 things, okay? So the first thing is a bit, okay? So this bit is either 0 or 1, okay? Now, as you can see, I put zeros, right? So 0 is the default value. So 0 basically means, this frame is not recently accessed. Okay, so you will understand what this recently means in a little bit, all right? But that's sort of the idea, okay? And if this bit is 1, then it indicates that it's recently accessed, okay? All right, so that is the first thing, the first extra thing maintained by the algorithm. And the algorithm also maintains another thing. You know, the name of the algorithm is clock, right? And what do we have for a clock? We have hands, right? Our the you know, 3 hands, right? Um, so here we will maintain a pointer. So that's our sort of like our hand, okay, the hand of the clock, all right? So this hand is going to move in a round robin manner, right? So it's going to move from the first position to second position, and then to the third position, and then um, it will go back to the first position. Okay, so this is how the hand is going to move. Okay. So in the beginning, let's say the hand is initialized to the first position, the first frame of the pool. Okay. All right, now let's run the algorithm, right? So the first one, 17. Okay, 17. That's a hit. Sorry, that's a miss. It's always a hit. It's always a miss, right? The first one. So 17 goes into um, a frame. So 17 has been recently accessed, and that's why we change this bit from 0 to 1. So once again, 1 means recently accessed, right? Every time you access the frame, you always set the bit to 1. Okay, later on, you will see when to reset it to 0, okay? But you want to create this um, notion of recency, right? So you want to sort of like achieve the effect that if the bit is 0, then it indicates, you know, it has not been accessed quite a while. Okay, so the next request is 28. Okay, so we have a miss. So 28 goes into a frame, and accordingly, you know, we change the bit. Well, pay attention, we never move the hand, right? You don't move the hand when things are good, right? So you move the hand only when, you know, you have to empty something. This is something you will see later. Okay, so the next one is 13. Again, a miss. It goes into an empty frame, and now we've got we flip the bit from 0 to 1. Okay. All right, let's do the next one. Here we've got 17, and that's a hit. That is good. All right. So we want to set the bit to 1, but it's already 1, so it doesn't change anything. Okay, but just so you know, every time you access a frame, you always set it to 1. Okay, the bit to 1. Okay, so this is called a use bit. A use bit. It's been used. Okay. All right, now let's continue here. So the next one is 53. Okay, so now our buffer is full, our pool is full, so we have to empty something. Okay, now we start to look at the element that is referenced by the hand. You know, so our hand is pointing to 17, right? So we want to evict 17, but no, look at the bit, right? So the bit is 1. Okay, so if it's 1, we give it a second chance. Okay, so the hand points to you, so you are the candidate for removal. But if your bid is 1, and then we give you a second chance. Okay, however, we will set it to 0 now. Okay, we'll set it to 0. All right. So after that, we have to move the hand. Okay, so sort of like we have punished 17. Okay, by flipping its bit, by resetting its bit to 0. Okay, but we don't actually remove it. Okay, so the next one goes to 28 again. You know, this is the guy under danger now, but its bit is 1, right? And therefore we don't do the removal right away, but we reset its bit. Okay, and then we move the hand. Okay, so the hand moves down to 13. Same thing, right? We want to remove 13, but we cannot because its bit is 1, and therefore we reset it to 0. Okay, but we have to remove somebody, right? Class, we have to remove somebody. So what do we do? Okay, so round robin, right? So the hand comes back to 17. Now this time we say, hey, we knew you had a 1 before, but we gave you this chance, and we saw that everyone had a 1. So now coming back to you, and you're the next one, as indicated by the hand. So sorry, you have to go. Okay, so that's basically what we say to 17. Okay, so that's why we remove 17, and we make an empty space, and 53 sits here. Okay, so don't forget 53. You have to reset the use bit. Okay, we just used it. Okay, so this is the current buffer pool. Okay, good. So now look at the hand, right? So the hand, we just removed 17, right? We removed 17, so we have to move the hand to the next position. Okay. You want to do this, right? Because you don't want to you don't want the hand to stay at 53. Otherwise, it's meaningless, right? And next time the bit of 53 will be reset to 0 immediately, right? But that doesn't make any sense, right? You want to sort of like let this block hang around a little bit, right? Because it's just been used, right? Okay. So we move down to the next one. The next one is 28, so that's a request. Okay. Oh, good. All right. So 28 really needs this. Why? Because 28 is in some sort of danger, right? Because this is the frame that the hand points to, right? And also 28, as you can see, right, its bit is currently 0, right? So that's a dangerous sign. Okay, so what you want to do is you want to switch this from 0 to 1 because we just used it, right? So this really comes to rescue. Okay. But you don't move the hand. Now remember, you move the hand only if you want to empty something. Okay. Now you come to 109. 109, we got a miss. Okay, so we move the hand. The hand still is at the position of 28, right? So we have to stick to the algorithm. You don't ask me, hey, why didn't you move the hand? 28 was accessed at time 6, right? Why didn't you move the hand? We do not move the hand. I said this, right? I said you move the hand only when you want to empty something, right? So that's just how the algorithm runs. Okay? You have to stick to it, right? You cannot really, try to be creative here. Anyway, so we come to time 7 and we got 109. And yes, this time you have to empty something. So that's when you move the hand, right? So you move the hand. No, sorry, actually you process the element, you try to punish the guy at the hand before you move the hand, right? So you look at 28 and you try to remove it, but then you see it's 1 here. So you give it a second chance and you flip the bit to 1 and then you move the hand. Okay, so you do something first and then you move the hand. Okay, so now the hand goes to 13. 13, the bit is 0 and you are the guy. Okay, so 13 is gone. And 109 is in. Okay, so the bit is 1. Okay, it's the blue color here. Okay, all right, so now you are done with 109, so you want to move the hand to the next one, round robin, right? Okay, all right, so that's time 7. Now, continuing, so you have 13 as the next request. That's a miss. Therefore, you have to empty something. Okay, so you look at the hand, it points to 53, but its bit is 1, so you give it a second chance. So you complete what you have to do, and then you move the hand. Okay, so 20A this time, right, it had its chance. But now, it's the next one. It's time to go, right? So 28 is gone, and then 13 takes its place. Okay, so the bit here is 1. Okay, all right, so you've done with this. You're done with this, so you move the hand, right? So the hand points to 109. Okay, you got the idea already, right? So you have 17 here. You have to empty something. So 109, so its bit is set to 1, set to 0, sorry. You move the hand, and the hand points to 53. So 53 will have to go. 17 comes in, and the bit is 1, and then you are done with this element, and then you move the hand to 13. Okay. So finally, we come to 28. That's a miss. So you don't remove 13, but you have to reset its bit to 1, to 0. You move the hand down to 109, and this is the guy to kick out. So you put 28 here, and the bit should be 1. Okay, and finally, the hand moves to 17. Okay, so that's the demonstration of this algorithm. So let's go back to look at the text. At this point, I think the text should be much easier to understand. So as you can see, for every frame, right? For every frame, you maintain a use bit, right? Technically, you need this bit only for a non-empty frame. So I demonstrated in my demonstration, even if the frame is empty, I put this bit 0 there, right? But that's innocuous. Is what I mean, innocuous, harmless, right? Anyway, so this use bit, what's really important is if it's 1, then it indicates that the frame has recently been requested. This recently, I mean, in some informal sense, right? This is not a very strict sense, but informal sense, this means, sort of like in one round of uh, cycle, right? So think about the hand movement, right? So this is really like it's really like a clock, right? So hand movement from one position, and then it goes over all the frames, and then it comes back to the same position, right? So that's like one round, right? So if it's 1, and then it means it's in the past round, it has been accessed. Okay, otherwise it would have been 0, right? Okay, so if it's 1, then it says it has been recently requested. Otherwise, it has not been requested for quite a while, right? So basically for one round at least. Okay, so every time you want to access a frame, you have to remember to set the bit to 1 in order to honor, the guarantees here, to achieve the guarantees here. Okay. All right, so we also maintain a hand, as you already know. So you use the hand only if you want to empty something. Okay, so the procedure is here. Okay, so first of all, if you check the frame that the hand points to, right? So if the frame has a use bit 0, and then this is the guide to go, you already know, right? So after you are done with this, remember you have to advance the pointer to the next frame, and this is in a round robin manner. So if the use bit is not 0, then it's 1, right? In this case, you basically give the frame a second chance. You say, okay, now this time I'm not going to remove you. But if I come back to you still, you have not been accessed, and then I'll remove you, right? So that's basically the idea. So you reset the frame's use bit to 0, and then you advance the pointer to the next frame, right, in a round robin manner. And then you go back to 1, okay? So you already know the algorithm, okay? All right, so we've already talked about all the algorithms, including one optimal but hypothetical algorithm that cannot be implemented, and 3 algorithms that can be implemented. All right, but before we go, I want to make several remarks. So first of all, if you look at the total number of misses for clock, right, it's 8. You see what I mean? You still remember how many misses are how many misses we got for each of the four algorithms. For Bellody, we got 6, and then for FIFO, we got 7, and then for LRU, we got 9, right? And for clock, we got 8. I can tell you the relative superiority among the four algorithms. The only thing you can say for sure is that Bellody will have to be the lowest, right? So because Bellody is an optimal algorithm, right? Okay, when everything is read, right? And all the requests are read, that's the best algorithm. Okay, so provably the best. So that's why 6, right? It's lowest. However, among the other 3 algorithms that I talked about, FIFO, LRU, and clock, there are no guarantees about their relative superiority, right? As I said, a lot of people think, I don't know why they think that way, but many people actually hold the misconception that FIFO is inferior to LRU theoretical, right? That's not true, right? As I said, you witnessed an example, right? So LRU can be worse than FIFO, okay? But in general, the superiority among these 3 algorithms is not certain, okay? So you can construct another sequence, for example, in that sequence, LRU turns out to be the best. That's very possible. Okay. In fact, we would talk about this in a tutorial. Okay. All right. So that's the first remark you want to know. The second remark is that there is some flexibility you can exercise in reality. This is because sometimes it would make sense to say some blocks are particularly important, so we don't want them to get removed, right? So in this case, what the database system does is to ping those blocks in the buffer pool, okay? So when a block is pinged, and then this is not a candidate at all for replacement. So this is to say that when you do buffer replacement, when you run one of those algorithms, you can imagine that the algorithm is executed only on the unpinned frames, okay? So later when we talk about John algorithms, you will see, the algorithm will have to ping certain frames in the buffer because you will need to access them again and again. Okay, so this is echoing what I said before. If you think about fact number 2 at the beginning of the lecture, right? I said if you talk about the same query, it sometimes will have to read the same block again and again. So you will see it when we talk about join algorithms later. So in this case, you simply ping those frames in the buffer, okay, so that they won't be removed. Okay, so remark number 3, okay. There is potential danger of information loss if you are not careful. Okay, why? Because the buffer pool sits in the main memory, right? But main memory is vulnerable to loss cuts, right? So when you lose power, all the information is gone, right? So that's a real danger if you think about it, right? So just imagine you give me $1, right? So my account should be credited with $1, right? So it should go up by 1. So the database will have to perform a write, right? But before this block can go from the buffer to the disk, let's say you have a power loss. So what's going to happen to my $1, right? And such a thing cannot happen, right? Simply cannot happen, right? So, but how? I mean, come on. So you, if you just leave the information in the main memory, I mean, and then bad things can happen, right? So this creates a non-trivial issue, right? You can do buffering, but the thing is, you also have to do something else in order to protect the information. Okay, you have to make sure, even though you are doing buffering, even if there is a power cut at any moment, still you cannot lose any information. I know at this point it sounds magical to you, right? Very difficult to believe how this can actually happen, right? So there are tricks. Okay, so this is something that we're going to talk about in recovery. Actually, uh, this will be discussed toward the end of the semester. Okay, so will be covered by Professor Surev. But as you will see, there are tricks to guarantee no information will be lost. So that's everything for today. Thank you very much for listening.